last week I had introduced the Schrodinger equation for spherically symmetric systems and discussed the properties of angular momentum and also the hydrogen atom and corresponding orbitals. In this lecture, I want to introduce you to the idea of solving the radial component of the wave function for spherically symmetric systems, because not all potentials are such where analytical solutions are possible like they were for the hydrogen atom. So, this lecture is going to be devoted to numerical solution of the Schrodinger equation for the radial component of psi. So, you recall that the Schrodinger equation for 3-dimensional potentials was like this: V as a function of only r, no vector, which is for the spherically symmetric potential, and this operating on psi gave you E psi. So, in this equation V r is spherically symmetric, and this is something that we have talked about in the previous lectures, and therefore, the wave function psi as a function of r vector can be decomposed through separation of variables as r, y, L m, theta and phi, where y L m's are the eigenfunctions for the square of the angular momentum y L m theta phi, eigenvalue being L L plus 1 h cross square, and also of the z component of the angular momentum, which comes out to be m h cross y L m theta and phi. We have discussed all this in the lectures last week. What we want to focus on here is numerically on getting the solution of R. So, as you can see from the discussion so far, y L m theta and phi are the same for all V r, and therefore, only R depends on the form of V r, and last week we had solved for R for very limited cases for the hydrogen atom potential. Now, what we want to do now is solve this for a general V r. To facilitate the solution, we had written R as a function u r over r, so that only the second derivative of u appears in the equation, and I will quickly write what the equation came out to be. It came out to be minus h cross square over 2 m u double prime plus L plus 1 times L h cross square over 2 m r square u, and now I am going to write u L, because this depends on L. R is a function of only the radial coordinates, plus V r u L r equals E u L r. This is the Schrodinger equation that we want to solve, and then the wave function psi r is given as u L r. Let me also include an n out here. So, I am going to write this as u n L r over r y L m theta and phi. So, our focus is on u in this case, and we had derived some general properties, and that was that for ul, ul r goes as r raised to l plus 1 as r tends to 0, and for potentials that die off as r goes to infinity. So, V r that go to 0 as r goes to infinity, u r goes as e raised to minus square root of 2 m mod e over h cross square r. This we had derived. So, what we want to do now is solve this numerically. Recall the one dimensional cases. What we had done there, for a general potential in x direction, we had taken a box which was a huge box of size L, so that the boundaries were really far off, and taken the wave function psi x to be 0 at the boundaries, and then built up the solution from both sides, and then matched the boundary condition in the middle. What did we do in that case? We said, let us take psi, let me call the solution coming from the left side as psi left x, and we also calculated psi right x, and in between at a point some x naught, we said that we should have psi L prime x, L means left here, over psi L x should be equal to psi r prime x over psi r x for the correct eigenvalue E, and that is how we build the solution. We are going to do exactly the same thing for spherical potentials. So, we do exactly the same thing for spherical potentials. So, let me take you through the numerical solution procedure step by step. So, step 1, I am solving the equation minus h cross square over 2 m u double prime plus L plus 1 h cross square over 2 m r square u plus V r u equals E u. So, number 1, step 1 would be to rescale the distances and energies in such a way that the distances become of the order of 1. So, I am measuring r 1, 2, 3, 4, 5 and so on, and so does the energy. I will illustrate this through an example. So, let us take the example of hydrogen atom, or let me write hydrogen like atoms or ions. That means, V r is going to be of the form z e square over 4 pi epsilon 0 1 over r with a minus sign in front. So, my equation for u is going to look like minus h cross square over 2 m, let me write the double prime explicitly, d 2 u over d r square plus L plus 1 h cross square over 2 m r square u plus V r, which are now I am going to replace by minus z e square over 4 pi epsilon 0 u over r equals EU. Now, obviously, for bound states E is going to be negative. E is less than 0. So, I am going to rewrite the equation as minus h cross square over 2 m d2u over dr square plus L plus 1 h cross square over 2 m u over r square minus z e square over 4 pi epsilon 0 u over r equals minus mod of E u. Now, first thing I want to do is rescale the distances. Now, here what do I have the parameters that are small in whose terms I should write the distances. So, I have the mass of electron, I have the Planck's constant h bar, and I have z e square over 4 pi epsilon 0. These are the three external parameters that determine the problem. Now, otherwise, if I do not rescale, you see the order of magnitude m is of the order of 10 raised to minus 30 kilograms, h is of the order of h cross is of the order of 10 raised to minus 34 kg meter square second inverse, and this quantity is of the order of 10 raised to minus 38 times 9 times 10 raised to 9. So, that is of the order of 10 raised to minus 28. These are very small quantities. I cannot really take r to be in this order. So, the way I rescale is I am going to write r is equal to some scaling factor a times x, and scaling factor a should be in terms of the mass h cross and z e square over 4 pi epsilon 0. So, let me write this a, which has the dimensions of length in terms of mass of the electron time raised to alpha, the Planck's constant raised to beta, and z e square over 4 pi epsilon 0 raised to gamma, and determine alpha, beta and gamma by dimensional analysis. You do that, and what you get is that A is going to be equal to 4 pi epsilon 0 h cross square over z e square m. This is of the order of Bohr radius, or 10 raised to minus 10 meters. So, now I am going to write r in terms of this A. So, I have minus h cross square over 2 m d2 u over dr square plus L plus 1 h cross square over 2 m r square u minus z e square over 4 pi epsilon 0 u over r equals minus mod E u. Let us write r equals a x, so that this becomes minus h cross square over 2 m 1 over a square d2 u as a function of x over dx square plus L plus 1 over 2 m a square h cross square over x square u x minus z e square over 4 pi epsilon 0 a u x over x equals minus E over nothing over times u, minus E times u. Now, substitute the value of A. So, you get minus h cross square over 2m z square e raised to 4 m square over 4 pi epsilon 0 square h cross raised to 4 u double prime, where u double prime, let me write it here, u double prime now indicates d2u over dx square plus L plus 1 h cross square over 2m, again z square e raised to 4 m square over 4 pi epsilon 0 square h cross raised to 4 u over x square minus z e square over 4 pi epsilon 0, 1 over a is going to be z e square m over 4 pi epsilon 0 h cross square u over x is equal to minus mod e u. You simplify all this and you get minus z square e raised to 4 m over 2 4 pi epsilon 0 square h cross square u double prime plus L plus 1 over 2 z square e raised to 4 m over 4 pi epsilon 0 square h cross square u over x square minus z square e raised to 4 m over 4 pi epsilon 0 square h cross square u over x equals minus mod e times u. Notice that naturally this quantity which I am encircling by red is unit of energy. You can easily check that, because this is nothing but z square e square over 4 pi epsilon naught a, which is nothing but the electrostatic energy if two charges are at a distance a. So, this is a natural unit of energy. So, you take it to the other side and you get u double prime minus a half u double prime plus L plus 1 over 2 x square u minus 1 over x u equals minus mod e over z square e raised to 4 m divided by 4 pi epsilon 0 square h cross square u. That is the equation. So, the equation you get finally looks like minus 1 half d2u over dx square plus L plus 1 over 2 x square u minus u over x is equal to minus this rescaled, let me call this energy E prime u, where E prime is nothing but E divided by z square e raised to 4 divided by 4 pi epsilon 0 square h cross square. Now, you see this equation looks very simple. All these constants have been taken into the units of distance and energy. Step 2, after rescaling the equation appropriately, I gave you the example of rescaling the hydrogen atom equation. There could be some other equations where you have to rescale it slightly differently. So, appropriately whatever rescaling you do, now divide r equal to 0 to some r equals r, where r is sufficiently large. Divide this interval into small intervals of some delta r, right. So, what we are doing is, here is my r equals 0, and I am taking a large distance out where wave function is supposed to vanish. So, this distance is r, and I am dividing this whole thing into what is called a mesh of small delta r intervals to integrate the equation. So, each of this interval is delta r, and what I will do, like the equation for one dimensional systems, this is essentially a one dimensional like system. I will start integrating from r equals 0 onwards, I will start integrating from r equals capital R inwards, and somewhere in between I will match the solution. So, what do I do now? Step 3, take u r to be 0 at r equals r, and that is why it is important that capital R be very large, where wave function essentially vanishes, and take u prime r equals r to be some finite number and start integrating the equation inwards. I have told you how to integrate the equation in the case of one dimensional potential. So, you may have to go back and see how it is done. So, essentially what you do is you take a u and take u I plus 1 to be equal to u I plus or minus, depending on whether you are integrating in or integrating out, delta r times u I prime. U I prime you again update by delta r u I double prime, and you now update, or this is I plus 1, u I plus 1 double prime you update through the Schrodinger equation. Because this depends on the value of u at that point. So, you start integrating inward, and you also take u r to be 0 at r equals 0, because recall that u near r equals 0 goes as r raised to L plus 1. So, even for L equals 0 it is 0, and you start integrating out. So, again you do u I plus 1 equals u I plus delta r times u I prime. Now, here since you know the behavior, you can take some help from there. U at r equals 0 goes as r raised to L plus 1. So, you can also write u prime equals L plus 1 r raised to L, and start building up your solution from first and second point onwards. And then step 4, at some intermediate point r naught. So, r naught is greater than 0, less than r, match u prime coming from r out divided by u r out at r equals r naught to u prime r coming in divided by u r coming in. So, these are to indicate two different solutions you are developing at r equals r naught. When the two logarithmic derivatives match, and I have to say it within some predefined accuracy. You will never get them to match perfectly. You can say they match within 10 raised to 3, 10 raised to minus 4, 10 raised to minus 3, or so on for certain E. That E is the eigenenergy. So, you found your eigenenergy, then you rescale and again normalize the wave function and all that. Now, I have given you steps to do this. You will have to practice it yourself. I cannot do more than this, and the best way to learn it is to practice it yourself. Take whatever help you have from available softwares, whatever language you know, but try to make this mesh yourself. Try to write the integrating software yourself and solve it. And then after this, step 5 obviously is then step 5, make U continuous through R naught, that means you match them again and normalize. And that gives you the solution of the problem. You scan over E, start from a very largely negative energy, and you start scanning and you will find solutions for different energies, many eigenenergies, many eigenfunctions, and then you order them according to the energy eigenvalues you are getting. So, this is for you to practice and learn. Beyond this, there is not really much to do in numerical integration of Schrodinger equation. So, to conclude this lecture, solving the 3-dimensional Schrodinger equation for spherically symmetric potentials is like solving the 1-dimensional Schrodinger equation with V effective R equals L plus 1 H cross square over 2 M R square plus the V R that is given. And then the technique, the numerical technique therefore is exactly the same as for the 1-dimensional Schrodinger equation, and that is what I have discussed in this lecture. So, this concludes basically our discussion of solution of the Schrodinger equation for spherically symmetric potentials. From next lecture onwards, I am going to concentrate on another system which is free electron like, but now we will have periodic potentials there, and therefore, that solution differs slightly from the free electron solutions and gives rise to bands.